Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we are going to discuss row operations. So in this topic, we will review the operations that can be performed on a system of linear equations. We will find equivalent operations on augmented matrices, and these will be called row operations. We will see that row operations can be undone. We will describe these row operations and introduce the concept of row equivalence. We will see that row equivalent augmented matrices have the same solution. Alright, up to this point, we can solve a system of linear equations if the corresponding augmented matrix is in row-echelon form. From that matrix, we can determine if there are no solutions, is one unique solution, or are infinitely many solutions. We've also seen algorithms that can find those solutions. Question: what if the augmented matrix is not in row-echelon form? Now, here is a common problem-solving technique that is used often in engineering. We have a difficult problem. We would like to find a solution to that problem. However, for whatever reasons, that problem is too difficult to solve. Instead, what we will do is we will transform the difficult problem into an equivalent problem that can be solved. We can then solve that equivalent problem and then interpret that solution appropriately to find a solution to the original problem. That is, we will transform the solution back into a solution to the difficult problem. So, in this case, given an arbitrary system of linear equations, we would like to find a solution, if one exists, to that system of linear equations. Problem is, this is too difficult a problem to solve. So instead, what we will do is we will transform the augmented matrix that is currently not in row-echelon form into one that is. And these transformations will be through a sequence of row operations. Next, we already know how to find the solution to a system of linear equations if the matrix is in row-echelon form. Not a problem, we can do that. Now we have a solution to that transformed problem. Now, fortunately, in this case, we're actually very lucky. The solution to the system of linear equations that is in row-echelon form is actually the identical solution to the original system of linear equations. And we will prove that. So these are the steps we will take. We will transform the problem into row-echelon form. We will then determine if solutions exist. If they do, we will then use backward substitution to find that solution or solutions. And it will turn out that those solutions continue to be the solutions to the original system of linear equations. Now, you will recall that when we were solving a system of linear equations, there were certain operations that we could perform without changing the solution. For example, given this system of two linear equations and two unknowns, if I was to simply swap the two equations, it wouldn't make a difference to the solution. A solution to the first is a solution to the second. Alright, let's see what this does to the augmented matrices. So here's the augmented matrix of the first system of linear equations. Here's the augmented matrix of the second system of linear equations. How did we get from one augmented matrix to the other one? Well, all we did was we swapped the two rows. All right, we're going to represent this operation of swapping two rows by the following symbol. Here we see a capital R italicized, and we are indicating that we are interchanging rows 1 and row 2. Now, the row operation of swapping row I and row j is denoted by the following symbol, with the capital R italicized, and the subscript suggests that row I and row j are being interchanged. If AB is an augmented matrix and you want to show this operation applied to this augmented matrix, you could write this as follows. The symbol would appear to the left of the augmented matrix. This is the same way as if you had, for example, a real number, 4.9, and you'd like to apply sign to that value. You would write sign to the left of 4.9, and that would imply that the sign function is being applied to the real value 4.9. Same way here. The symbol you see here to the left of the augmented matrix indicates that that operation is being applied to that given augmented matrix. As an example, I could apply the row operation that swaps row 1 and 3 to the matrix that you see on the left. That is equal to the augmented matrix on the right. And as you can see, the augmented matrix on the right has rows 1 and 3 swapped. Now, there's another acceptable operation. What we can do is simply multiply any of these equations by a non-zero scalar. So in this case, I have multiplied the second equation by the non-zero scalar -3. Well, if x1 and x2 satisfied the original second equation, then x1 and x2 must continue to satisfy the second equation now that we've multiplied both sides by -3. Let's see what that does to the augmented matrix representation of these systems of linear equations. So here we have the system of the augmented matrix representing the first, and the augmented matrix representing the second. Well, as you can see, all that really happened is we multiplied the second row by the non-zero scalar -3. And we will now represent this by the symbol -3 dot row 2. This indicates that we will be multiplying row 2 by -3. The row operation of multiplying row I by a non-zero scalar alpha is denoted by the following symbol, where the R is capitalized and italicized, and the subscript indicates that alpha is multiplying row I. Now, if AB is an augmented matrix and you want to show this operation applied to this augmented matrix, you can write the symbol to the left of the matrix. So, for example, here we have an augmented matrix on the left, and it is being applied to it is the operation of multiplying row 2 by 2.5. And that, of course, is the matrix you see there on the right-hand side of the equal sign. Now, a final operation that we can perform on a system of linear equations is to add a multiple of one equation onto another. So, for example, here I am adding 3 times equation 1 onto equation 2. So, 3 times 3 plus -8 is 1. 3 times 5 is 15 plus 4 is 19. 3 times 16 is 48. minus 7 is 41. And again, let us look at the augmented matrix representation. That is the original system, and this is after we have performed the operation of adding 3 times equation 1 onto equation 2. Well, taking a look just at these two augmented matrices, it's quite clear that all we did here was add 3 times row 1 onto row 2. And once again, we will represent this by the following symbol. So we are adding 3 times row 1, and that is added to row 2. The row operation of adding a multiple alpha of row I onto row j is denoted by the following symbol, with the italicized capital R, and the subscript suggests that alpha times row I is being pushed onto or added to row j. Once again, if AB is an augmented matrix and you want to show this, you place this symbol to the left of the matrix. For example, if we wanted to apply the operation of adding twice row 3 onto row 2, you could do so as follows for the matrix on the left. So that operation applied to that matrix gives us the matrix on the right, where the second row has now the entries 0, 2, 4, and 4.2. Consequently, given an augmented matrix, there are now 3 operations that we can perform on that augmented matrix. We can swap row I and row j. We can multiply row I by a non-zero scalar alpha. And we can add a multiple alpha of row I onto row j. And each of these operations is represented by the corresponding symbol on the right. All right. Now, here's another question. Can we always undo a row operation? So, for example, if I apply a row operation onto an augmented matrix, is there another row operation that gets us back to the original augmented matrix? So, undoing a swap. Suppose we have an augmented matrix AB and we have applied the operation of swapping rows 3 and 5. How do we undo this operation? How do we get back from the new matrix that has the rows swapped back to the original matrix? Well, with a little thought, all we have to do is swap rows 3 and 5 again. So this is going to be denoted as follows. If we swap rows 3 and 5 of the matrix that results of us swapping rows 3 and 5 of this particular augmented matrix AB, we get back the matrix AB. So this is the operation of swapping rows 3 and 5 of the matrix AB, and that results in another augmented matrix. Then, when we apply the same operation again, then we swap those 2 rows again, which gives us back the original augmented matrix on the right. This is a little bit like writing down that ln of e to the x is equal to x. E to the x calculates the exponential for that particular value of x. The inverse operation of the exponential function is the logarithmic function, and so therefore ln of e to the x is equal to x. The only difference here is that it is the same function or the same operation that is undoing the original operation. Thus, we may write the inverse of the operation of swapping rows I and j is just the operation of swapping rows I and j. Now, suppose we have an augmented matrix AB and we apply the operation of multiplying row 7 by negative 1.25. How do we undo this operation? Well, if I multiplied, say, the entry 2 by negative 1.25, that would give me the result of negative 2.5. How do I get back from negative 2.5 back to 2? Well, I just have to multiply that same row by the reciprocal of negative 1.25, which is negative 0.8. So we can say this as follows. First, this is the application of multiplying row 7 by negative 1.25. This results in a new matrix. However, if we now apply the operation of multiplying row 7 now by negative 0.8, we will get back to the original matrix because we have undone the operation. As you remember, we explicitly required this operation to have a non-zero scalar. So this operation does not allow you to multiply, say, row 7 by 0. Most importantly, because you cannot undo that operation. Thus, we may write that the inverse operation of multiplying row I by alpha is multiplying row I by the reciprocal of alpha. Finally, suppose we have an augmented matrix AB and we have applied the operation of adding 2.7 times row 1 onto row 5. How can we undo this operation? Well, to get back to the original matrix, if we just added 2.7 times row 1 onto row 5, doesn't it make sense that all we have to do is now add negative 2.7 times row 1 onto row 5? That makes sense. So once again, we will write this as follows. If we were to add 2.7 times row 1 onto row 5 and apply that operation to this given augmented matrix, this would result in a new matrix. And if to that new matrix we then applied the operation of adding negative 2.7 times row 1 onto row 5, we would get back the original matrix that we see on the right. Thus, we may write that the inverse operation of adding alpha times row I onto row j is adding negative alpha times row I onto row j. Thus, we now have 3 row operations, and each of these row operations has an inverse, and that inverse is of the same form as the original. So to undo a swap, we just perform the same swap. To undo the multiplication of row I by alpha, we multiply row I by the reciprocal of alpha. To undo adding alpha times row I onto row j, we add negative alpha times row I onto row j. Now, what's important about row operations is that if we have an augmented matrix and it has a solution, or not a solution, then applying a row operation to that augmented matrix does not change the solution, or lack of a solution. So, for example, suppose we start with this augmented matrix here. There is in fact one unique solution. However, note that if we were to apply the row operation of adding negative 0.6 times row 1 onto row 2, we would get the matrix on the right. Now, because that row operation does not change the solution to the matrix on the left and the matrix on the right is the same. Now, if at the same time I apply another row operation to the matrix on the right, say add 0.6 times row 1 onto row 3, I now get the matrix on the right. Now, the solution to this matrix is equal to the solution on the left, which is equal to the solution of the first matrix. Finally, if we take the matrix on the right and we now apply the operation of adding negative 0.8 times row 2 onto row 3, we get the final matrix in the lower right-hand corner. The solution to this matrix is the same as the solution to every other matrix you see here. So, if I apply any number of valid row operations to a matrix, I am going to end up with another augmented matrix that has the same solution. So what we're going to define is a concept of row equivalence. Consequently, we now have the following definition. Two augmented matrices are said to be row equivalent if there exists a sequence of row operations that transform one augmented matrix into the other. If two augmented matrices AB and CD are row equivalent, then we will write that they are row equivalent with the tilde symbol between them. So this should be read as the augmented matrix AB is row equivalent to the augmented matrix CD. Now, recall 3 of the 4 properties of equality. First of all, reflexivity. X is equal to X. Second property, symmetry. X is equal to Y if and only if Y is equal to X. And the third property, transitivity. If X is equal to Y and Y is equal to Z, then X is equal to Z. Note that the same is true for row equivalence. First of all, there is a sequence of row operations, specifically no row operations, that take us from the matrix AB to the augmented matrix AB, and therefore both of these matrices have the same solution. Now, if the augmented matrix AB is row equivalent to the augmented matrix CD, then there exists a sequence of row operations that take us from AB to the augmented matrix CD. However, we have seen that every single row operation has an inverse operation, and thus it makes sense that we could apply the inverse operations, specifically in the reverse order, to get back from the augmented matrix CD to the augmented matrix AB. Finally, transitivity. If an augmented matrix AB is row equivalent to an augmented matrix CD, there exists a sequence of row operations that take us from AB to CD, and thus they have the same solution. But if there is a sequence of row operations that take us from CD to the augmented matrix EF, then there exists another sequence of row operations that does that transformation, and therefore CD and EF have the same solution. But if you were then to apply all the row operations that got you from A, B to C, D, and then applied those row operations that got you to E, F, that would bring you from A, B all the way to E, F. And consequently, the solution to A, B will be the same solution as the solution to E, F, and we will say that AB is also row equivalent to EF. Now, when we are performing a sequence of row operations on a matrix, we will use this concept of row equivalence. So what we will write on the board is as follows. Suppose we swapped rows 1 and 2. Well, in this case, both of these matrices continue to have the same solution because the only difference between them is that we applied a row operation. Therefore, we will write that these two matrices are similar. If we want to emphasize how we got from the matrix on the left to the matrix on the right, we will write below the equivalence or the row equivalence symbol the operation that was performed, in this case swapping rows 1 and 2. If we then were to go on to multiply row 2 by 1.5, we would again indicate that the new matrix is row equivalent to the previous matrix, and the operation that got us from the second matrix to the third was multiplying row 2 by 1.5. Notice that we could also write this as follows. If we first applied the operation of swapping rows 1 and 2 to the given matrix, and then multiplied row 2 by 1.5, we would get the matrix on the right-hand side. Notice that the order in which row operations occur may affect the result. For example, getting from the matrix on the left to the matrix on the right by swapping the two rows, and then multiplying row 2 by -3 gives us the matrix on the right. However, if we were to start by multiplying row 2 by -3, we get the matrix we see here on the right, and then if we were to swap those two rows, we would get a new matrix. Notice that the matrices are different, so the order in which row operations are applied may affect the result. Now, one nice consequence, however, is that both of these final results are still row equivalent, because I can get from the last matrix to the previous matrix by swapping the two rows. Then I can multiply row 2 by -1/3 to get the matrix on the lower left. Then I can follow the previous sequence of row operations to get back to the matrix in the top right. So the solution to all of these matrices are the same because all of these matrices are row equivalent. Now, recall this diagram that we saw at the start of class. Finding a solution to an augmented matrix that is general is too difficult to solve. So instead, given an arbitrary augmented matrix, we will find a sequence of row operations that transforms the augmented matrix into one that is in row echelon form. From the previous lecture, you know how to find the solution to an augmented matrix that is in row echelon form, so you can then go ahead and find that solution. However, if we got from the arbitrary augmented matrix into the row-echelon form augmented matrix through only a series of row operations, then the solutions to both of those augmented matrices must be the same. Therefore, the solution we found for the augmented matrix, row-echelon form matrix, must be the solution to the original arbitrary augmented matrix. So, following this topic, you now understand the three row operations. You understand that if a row operation is applied to an augmented matrix, the resulting augmented matrix has the same solution. You understand that each row operation is associated with a symbol, and you understand that each row operation also has an inverse operation that undoes what that row operation did. You also know the definition of row equivalence and how it will be used in this class, and you understand that row equivalence is very similar to equality in at least some of the ways. Here are the references, acknowledgments, the colophon, and a disclaimer. Cheers!